Newton's Second Law of Motion by Madison Sipes, Kennedy Petrie, Tiana Bass, and Aidan Gunner. Meet our group. This is Tiana Bass, Madison Sipes, which is me, Aidan Gunner, and Kennedy Petrie.
Newton's second law of motion. Introduction. Newton's second law of motion is closely related to Newton's first law of motion. It mathematically states the cause and effect relationship between force and changes in motion. Newton's second law clearly states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. To get the wagon to accelerate, you have to apply a pull. If mass of the wagon increases and greater pull is necessary to accelerate it.
Application of Newton's second law of motion. Physics. Core application. Newton's second law is one of the most fundamental principles in classical mechanics. Usage. It explains how forces cause changes in motion, acceleration, forming the foundation for analyzing everything from falling objects to complex mechanical systems. Examples. Projectile motion, circular motion, and friction analysis in physics problems. Engineering. Mechanical engineering. Engineering uses the law to calculate the forces needed to move parts of machines or vehicles. Civil engineering helps in designing stable structures that can withstand forces like wind, earthquakes, or traffic loads. Electrical engineering. Newton's law is indirectly used in electromechanical systems such as motors and actuators. Biomechanics, healthcare. Medical fields, Newton's law is used to understand how muscles and bones work together to produce motion. Physical therapy helps design rehabilitation exercises by measuring the force and motion of limbs. Prosthetics. Engineers apply F equals ma to design prosthetic limbs that move naturally with the human body. Aerospace. Rocket propulsion. Calculating the required thrust force to accelerate spacecraft. Satellite motion. Understanding how small forces over time can alter satellite trajectories. Launch dynamics. Engineers use Newton's law to design launch systems that can overcome Earth's gravity. Automotive and transportation. Crash safety. Used to design safer cars by understanding how forces act on bodies during collision. Vehicle dynamics. Helps determine how forces from engines, tires, and brakes affect acceleration and stop distance. Road design. Applied in calculating safe turning, radius, and braking angles. Sports science, kinesiology. Athlete training. Coaches and trainers use the law to optimize performance by analyzing acceleration and applied forces. Injury prevention. Understanding forces on joints and muscles help prevent strain and overuse injuries. Robotics, motion control. Robots are programmed to apply the right force to achieve desired movements. Balance and navigation. Newton's law is used to ensure robots can adjust their forces to stay balanced or interact with objects.
In Objective 1.4, we have scientists who were involved in the discovery of Newton's second law. Here we present Sir Isaac Newton, who was the basic founder of the Newton's second law. He founded it in his space, which was commonly called the Principia. A fun fact about Sir Newton, he allegedly came up with the law after gravity was created, watching an apple fall from a tree. And also, a weird fact is Newton was once struck with a needle in his eye socket while doing a study on how light affects vision.
Galileo Galilei. His contribution to laying the groundwork earlier on were his studies in motion and acceleration. He also discovered that objects fall at the same rate regardless of mass, in a vacuum. The influence he had on Newton's second law of motion involved his introduction to the concept of inertia, which Newton expanded into his first and second laws. Galileo didn't work side by side very often with other scientists. His ideas strongly influenced and were supported by great minds of his time. Fun facts. Galileo dropped spheres of different masses from the Leaning Tower of Pisa to prove that falling objects accelerate at the same rate. Galileo invented an early version of the telescope and discovered Jupiter's 4 largest moons. Weird fact. He spent the last 9 years of his life under house arrest for his scientific beliefs and still kept writing. René Descartes, his contribution to the groundwork in Newton's second law were his ideas about momentum and linear motion. His work on conservation of motion and mechanical physiology influenced Newton's thinking, although Newton later corrected some of Descartes' assumptions. Famous quote, "I think, therefore I am." Fun facts. Created the Cartesian coordinate system, XY axes, that we use in math today. Also known for bridging philosophy and mathematics. Johannes Kepler. Johannes Kepler, his contribution to Newton's second law of motion were his laws of planetary motion, showing how planets move in ellipses rather than in perfect circles. His work helped Newton connect force, gravity, with acceleration, especially in celestial mechanics. Fun facts. Used Tycho Brahe's astronomical data without modern tools to calculate planetary motion. He also created the first science-based description of how vision works in the human eye. He's known for discovering that planets move in elliptical orbits, not perfect circles, as we said before. Christian Huygens, he worked on the concept of centripetal force and studied collisions. His studies helped develop early ideas about force and motion in circular paths, which Newton used and refined. Fun facts. Developed the pendulum clock, the most accurate timekeeping device of his era. Discovered Saturn's moon tie-in and explained Saturn's rings. Made early breakthroughs in wave theory of light. Robert Hooke. Robert Hooke proposed ideas on gravitational attraction and elastic forces, Hooke's law, to contribute to the groundworks of Newton's second law of motion. He corresponded with Newton and may have influenced Newton's thinking on gravitational force. Famous law, Hooke's law, which describes how springs stretch. Fun facts. First, he used the term cell to describe biological structures while looking at cork under a microscope. Was a fierce rival of Newton and claimed credit for early ideas about gravity. Experimental process of Newton's second law of motion. Newton's second law of motion is the relationship between force, mass, and acceleration in a variety of physical phenomena. The formula is F equals ma. The formula F equals m multiplied by a is where F is the net force, m is the mass, and a is the acceleration. The experiment process involves measuring mass, applying different force, measuring acceleration, and analyzing the relationship between force and acceleration. Original experimental process described of Newton's second law of motion. The original experimental process involved using a cart, applying a known force, measuring mass and the acceleration, and analyzing the relationship to establish F equals m multiplied by a. Force acceleration. Newton would apply a known force to the cart. This could be done by pulling it with a string attached to a weight that hung off the edge of a table. Measurement of mass. He carefully measured the mass of the cart and the weights used to create the force. Acceleration measurement. Newton would measure how fast the cart accelerated when the force was applied. This could be done by timing how long it took for the cart to travel a certain distance. Data collection. By varying the amount of weight, force, and measuring the corresponding acceleration of the cart, he collected data on how the acceleration changed with different forces.
Difficulties of Newton's second law of motion. Friction. In real-world scenarios, friction can significantly affect the net force acting on an object. Variable mass. In some situations, the mass of an object may change over time, such as in rockets as they burn fuel. This complicates the application of the law since the relationship between force, mass, and acceleration becomes more dynamic. Rotational motion. Newton's second law primarily applies to linear motion. When dealing with rotational motion, the concepts needed to adapt, introducing additional complexities such as torque and moment of inertia. These difficulties can make the application of Newton's second law less straightforward in practical situations compared to idealized scenarios.
Motivation for experiment presented for Newton's second law of motion. The motivation for experimenting with Newton's second law of motion stems from the need to understand the fundamental principles governing motion and forces. Validate theories. Testing Newton's second law allows us to confirm its validity in real-world situations, reinforcing our understandings of the relationship between force, mass, and acceleration. Enhance predictive power. Understanding how forces affect motion helps us predict the behavior of objects under various conditions, which is essential in fields like engineering, physics, and everyday life. Educational value. Conducting experiments fosters critical thinking and problem-solving skills, encouraging students to engage with scientific concepts actively.
In Objective 2.4, the original benefits of the discovery of Newton's second law of motion, we have the principles derived from the Newton's second law, which are applied to everyday life, such as various technologies from vehicles to spacecrafts. And we also have the understanding of interactions, which helps us understand how different forces interact, such as gravitational forces, frictional, and tension forces.
In modern settings, Newton's second law is demonstrated using advanced equipment. Setup and procedure. Modern experiments that verify Newton's second law often use air, tracks, or dynamic carts to reduce friction. A common setup includes air track or low friction cart, creates a nearly frictionless environment. The pulley system applies a known force via hanging weights. Motion sensors or photo gates can accurately measure acceleration. Data acquisition software captures and analyzes data in real time. Early scientists such as Newton and Galileo faced many difficulties when studying motion. They had poor lighting, no precise timing tools, and no temperature control, which hindered accuracy. The safety standards were minimal, and measurement tools lacked consistency and standard units. High friction and basic substances also made it difficult to accurately measure force and acceleration, problems that modern laboratories have mostly solved.
Differences in modern approach outlined. The goal of Newton's work was to better understand and explain motion in both everyday life and the universe. During the scientific revolution, thinkers such as Galileo challenged traditional beliefs, inspiring Newton to create a solid mathematical framework for motion. His work is designed to help astronomers predict planetary motion, engineers design better machines, and scientists and philosophers discover universal truths about how the world works. Advancements. These are the advancements.
Modern benefits of discovery explained. Newton's second law is important in modern fields such as engineering, aerospace, medicine, and robotics because it helps in the advancement of technologies such as vehicles, rockets, prosthetics, and drones. It is also important in simulations such as video games. Historically, it changed science and engineering by allowing for precise motion calculations, advancing technologies such as cannons, ships, and laying the groundwork for traditional physics during the Industrial Revolution.
In Objective 3.4, we discussed the future expectations of the research discussed, which is Newton's second law of motion, how the world plans to advance this law. So here we have nanotechnology, which is applied of Newton mechanics at the micro and nano scale. We also have space exploration, so we're planning to further that knowledge in space trajectory. And also educational tools, which could be the advancement of everyday books, such as the books that we read in class, and also just different researches that we can find online.
Our example question. A 10 kg door is pushed with a force of 50 N across the surface with 5 N of friction acting against the motion. What is the door's acceleration? Our motivation. To help students practice applying Newton's second law of motion, F equals ma, in real world scenarios, like relatable scenarios. Doors are everyday objects, and thinking about forces acting on them, like pushing and friction, makes the abstract concepts of net force and acceleration more concrete and understandable. The development. The question was developed by combining basic concepts from Newton's second law of motion with a simple real-world object, a door. The idea was to create a scenario that is easy for anyone to visualize, making the physics more accessible. I started by choosing a common item, the door, and giving it a reasonable mass, 10 kg. Then I introduced a pushing force, 50 N, to represent an action someone might realistically do. To make the problem a little more complex and realistic, I added friction, 5N, because in real life, surfaces are rarely frictionless. This way, students need to calculate the net force before finding the acceleration, encouraging them to think through the steps logically rather than just plugging numbers into a formula. Relevance of question to topic explained. The question we created directly relates to Newton's second law of motion. It states that the acceleration of an object is directly proportional to the net force acting on it and inversely proportionate to the mass, F equals ma. It aligns with the definitions and explanations presented early on in the course in regards to how forces affect the motion in objects. Previously, we discussed the relationship between force, mass, and acceleration, and how this law applies to real-world situations such as car crashes and everyday motion. The question reinforces these concepts by requiring students to calculate forces, acceleration, and masses.
Benefits on understanding question given. Learning to solve the given question improves the ability to gain skills in critical thinking, algebraic questions, and quantitative reasoning. These skills are important for physics, engineering, and other technical fields. Additionally, solving these problems help move beyond memorization by teaching how force, mass, and acceleration interact dynamically, helping to build a stronger foundation for understanding complex topics like friction, circular motion, and systems of force, all of which rely on Newton's laws. Identify force on door.
Process of writing question outline. When creating the question, we focus on applying Newton's second law of motion, F equals ma, in a way that involved real-world motion. We decided involving a question about a door being pushed was appropriate because it's a simple, relatable, and everyday task that still demonstrates core physics. We included friction in the question to show a more advanced method when applying the formula.
Here in Objective 4.4, we talk about the uniqueness of the question that we chose for our slide. We go with the basic formula used, F equals ma, but we also added a little twist to it where you have to perform a two-step process in finding the net force plus the acceleration, and then you can proceed with just the basic formula.
Relevant diagram for the example question. As you can see, the normal force equals 98 N, friction equals 5N, weight equals 98 N, 10 kg, and the applied force 50 N.
Relevant formulas and constant explained. In the example question, a 10 kilogram door is pushed with a force of 50 newtons, while 5 newtons of friction acts against the motion. To find the door's acceleration, who use Newton's second law of motion, F equals ma, where F equals net force acting on the door measured in newtons, m, mass of the door measured in kilograms, a, acceleration of the door measured in meters per second squared. Continue. First, we find the net force. The applied force is 50 newtons to the right, and the frictional force is 5 newtons to the left. Since friction opposes motion, we subtract it from the applied force. There's the formula. Now plug into Newton's second law. There's another formula. Substituting values, there's another formula. Thus, the door acceleration is 4.5 meters per second. Continued. Constants involved. We also use gravitational acceleration to understand the weight of the door if needed. There's that. Even though weight isn't directly needed to find acceleration in this case, because forces are horizontal, knowing the normal force, the force from the ground pushing upward, could be important in more advanced problems involving friction calculation. Continued. Reasonable ranges for variables. Force, usually between 10 newtons and 100 newtons for simple problems. Mass, 1 kilogram to 100 kilograms for everyday object like doors. Acceleration, 0.1 ms over 2 to 10 ms over 2. In normal classroom examples, gravitational constant, always about 9.8 ms over 2 on Earth.
Solving process theory described. Identify what is given. Mass of the door, M equals 10 kilograms. Applied force, F applied equals 50 newtons. Friction force, F friction equals 5 newtons. We use Newton's second law of motion, which states F net equals mxa. Solving process continued. The net force is the total force acting on the door, considering both the force pushing it and the friction slowing it down. Since friction acts in the opposite direction, we subtract it from the applied force. It will be F net equals F applied minus F parentheses friction. Substitute the given values, which would be F parentheses net equals 50 newtons minus 5 newtons, and then it'll come out to 5 parentheses net equals 45 newtons. Solving process continued. Solve for the acceleration. Now use the formula. F parentheses net equals m times a. Rearrange it to solve for a. A equals F parentheses net divided by m. Substitute the known values. A equals 45 newtons divided by 10 kilograms. So A will equal 4.5 ms square root. Solving process continued. State the final answer clearly. The acceleration of the door is 4.5 meters per second squared. Summary of the process. Write down given values. Recognize that friction opposes motion and subtract it from applied force to find the net force. Apply Newton's second law. Solve for acceleration. Clearly state the units and final answer.
Here in objective 5.4, we have the in solution, which is the correctiveness and the relevance of the question that we chose. So here we just discussed that our example question has come out to a correct answer on all ends, which particularly follows logical and standard physics practices.
Additional information over Newton's second law of motion. Think about this. Next time you hit the brakes, lift a box, or feel a roller coaster accelerate, Newton's second law of motion is working behind the scenes. Newton's second law is something we use every day and sometimes don't even realize it. Newton's second law took several decades before it became what it is today. So many scientists went into the beginning stages before Isaac Newton even had the thought in his head. They came up with these theories before him and didn't complete it until Isaac Newton came around. And he used some of their theories to really develop what it is today.
Additional student interest. We all collectively found it surprising how mass is not always constant. Why this is surprising, you may be asking? Most people think mass as fixed, but when you apply the law of rockets, jet engines, or leaking containers, you need a more complex version of the formula, showing how powerful and adaptable Newton's laws truly are.
Most important takeaway. The most important part of Newton's second law of motion is that it gives us a clear mathematical way to predict how objects move when forces are applied. This principle is essential for designing anything that moves, from vehicles and roller coasters to rocket and prosthetics. It connects theories to real-world application, making it a cornerstone of physics. Why the project matters. This project is valuable because it shows how a simple formula can explain complex systems in motion. It encourages critical thinking, connects science to everyday life, and lays the foundation for more advanced studies in mechanics, engineering, and technology. Understanding Newton's second law is not just academic, it's practical and powerful.
In objective 6.4, we have our site slide, which you can navigate to the slide if you need a little extra clarification on where we found our facts and different knowledge factors that we use in our slides.